Hey friends, we are in chapter 8. We're looking at section 8.2, and you saw the vocabulary that we're going to have in a moment, so I'm going to show you that in a second. We're talking about sequences and equations. Our textbook uses sequences to kind of bring about the concept of equations. Don't worry if it seems a little bit uncomfortable. We'll talk more about it in class, but take a look at what we've got. We've got some vocabulary words. We've got this concept of sequences, which I think will make total sense to you, and let's see how we do. So I'm looking at our vocabulary. We've got 4 vocabulary terms that we need to keep in mind. The first of which is the word sequence. The word sequence is an ordered list of numbers. You guys are used to sequences. Things like 5, 10, 15, 20, 25, 30, right? This is a sequence, 5, 10, 15, 20. This is a sequence. And we know when we talk about sequences, we know that oftentimes, well, they actually go on forever and ever, as is the situation that we have here when we count by 5s. Another thing about sequences that's really important is for us to recognize that each number in a sequence is ordered, and the order is determined by the term number. Like, this is the first number, this is the first term of the sequence. So 5 is a term, 10 is a term, 15 is a term, but 5 is the first term. 10 is the second term, 15 is the third, 20 is the fourth, so forth and so on. One of the things that you're going to often be asked when looking at sequences is you'll often be asked to figure out what the 90th term is or what the 10th term is. And sometimes it's easy just to continue along with the pattern, but sometimes you want an equation. So that's also going to be an important part of what we discuss. The next thing I want to discuss is the word term. Each number of the sequence is called a term, and each term is like numbered. So in a sense, they're called by their ordinal numbers, like first, second, third, but we'll call it the first term, second term, 1, 2, 3, 4. Okay. An arithmetic sequence is a particular type of sequence. Actually, this one is an arithmetic sequence. It's a particular type of sequence when each consecutive number has a common difference. Let's look at the example we had up there. So if I have 5, 10, 15, and 20. If you take 2 consecutive terms, let's say 15 and 20, and you find the difference between them, you would get 5. Well, that's going to be the same for any 2 consecutive means one coming right after the other, any 2 consecutive terms, we will find that we have a common difference of 5. By having a common difference between each pair of consecutive digits, we know that that is an arithmetic sequence. That's the definition of an arithmetic sequence. There's tons of other different types of sequences. You can make up sequences, but an arithmetic sequence has this special property. All right, common difference, as we discussed before, is just the difference between 2 consecutive terms in an arithmetic sequence. So that's it for our vocabulary. Let's take a look at some examples. Here we are at example 1. In example 1, we're asked to describe an arithmetic sequence. Describe each arithmetic sequence using words and symbols. So when we describe it with words, here's what we're really going to do. We're going to talk about what the common difference is. That's going to be important. When we describe it using symbols, we're going to write an equation. So we're going to look for words and we're going to look for an equation. First thing let's do, we're going to use this handy chart. So the term number refers to kind of the ordinal number of each of the terms in the sequence. So I've got the first term, second, third, and in this case we only have 4 terms listed, so 4 is enough. The first term is 6, the second term is 7, the next is 8, and the following 4th term is 9. So now what we're going to do is relate this together. So the words part of this really means that we're going to find the common difference. In order to find a common difference, we need to confirm the fact that we are going up incrementally from term to term, which we are. So the difference in term number is a positive 1, right? So from 1 to 2, 2 to 3, 3 to 4, we get a change of 1. Now when I'm looking at the difference in terms of the term, it also goes up by 1, right? Positive 1. By the way, the common difference, as we see here, the common difference is 1 for each term number that we go up 1 in the actual term. So the common difference is 1. By the way, common differences could be negative. So, and if it were, these numbers would be going down, right? So the common difference is equal to positive 1, which is important. And now we're going to explain this thing in symbols. So what can I do? So this is like old-fashioned, let's take X and Y, come up with an equation, a way to relate them, or find a rule for our situation. So we're going to try to find a rule. What can I do to this term number in order to get this term? but I need to be able to do the same thing for each. So what would I do with 1 to get 6, 2 to get 7, 3 to get 8, and 4 to get 9. You hear me saying 5 because I know the answer, right? So the answer is that I'm going to add 5, right? Simply adding 5. I don't have to multiply this by anything, or technically I can say I'm multiplying this by 1 and adding 5. That'll make sense a little bit later. But I'm basically I'm just adding 5 to the term number to get the term. So I'm going to use a variable. N is the term number plus 5, which we determined we needed in order to get to the term. So the equation that we have is n plus 5 is equal to t. The next one is not going to be as straightforward, but it won't be hard at all. We can handle it. If we notice that we've got, again, 4 terms, so I'm going to use my blue marker, 1, 2, 3, and 4, and those numbers are right in order, and I'm going to write down 4, 8, 12, and 16. Now that I have these listed, I'm going to do the same thing I did last time. For each change of 1 in the term number, right, that's a positive change of 1, I actually have a change of 4 in the actual term. You guys see that? So what this tells me is I look at this as a ratio. 1 to 1 gave me a common difference of 1. 4 to 1 gives me a common difference of 4. So my common difference, in this case, that's me explaining it in words again, is equal to a positive 4. The next thing we need to do is actually come up with an equation. I think many of you probably see the relationship already. The relationship here is if I take this number, what do I need to do to 1 to get 4? But I'm going to do that same thing to 2 and get 8, same thing to 3 and get 12, 4 and get 16. If you're not shouting it, I'm going to shout it for you. We're going to multiply the term number by 4. So it's going to be 4 times n is equal to t. So 4 times 1 gives me 4, 4 times 2 gives me 8, so forth and so on. Not too bad, right? Let's see if we can handle this in another example. So here we have in example 2, we're going to find a term in an arithmetic sequence. So this is going to be a little bit different. Again, we're going to use the skills that we developed before, but we're going to try to concentrate more on the equation portion, okay? Because that's going to help us, and I'll tell you why we'll use the equation in a moment. So we'll do the same thing. We've got 1, 2, 3, 4 terms given. Those terms are 7, 10, 13, and 16. We're going to figure out what the common difference is. So for each positive increase of 1 in terms of the term number, we have a positive increase of 3. So we see that the common difference is 3. Now here's my hint. Let's go back to that last example. You see that the common difference was 1 and we technically multiplied n by 1. You see that the common difference is 4 and we ended up multiplying n by 4. That's not coincidence. That's like some real mathematical concept called slope that we'll deal with later, changing y over changing x. But for now, let's just take a look at it as it is. So each time we have the common difference is 3 over 1, 3 to every change of 1 in the term number, then what we're going to do is think about multiplying n by 3. Ooh, I think I wanted to use green for that. So I want to multiply n by 3. I don't like how that looks. Just give me 2 seconds. And I'll say it again. I'm kind of a broken record right now. We're going to multiply n times 3. Better. All right, so now that we've done that, we've got to figure out. So 3 times 1 gives me 3, which is not 7. So I'm stuck because I need the term. I need to find something that's going to give me t. 3 times something. Yeah, 3 times 2 is 6. 3 times 3 is 9. That's not working. This 3 times n business doesn't seem to be working, but if we add something to it, maybe it'll help out. So if I do 3 times 1, that's 3, plus 4. Where did you get the 4 from, Dion? You're amazing. She's a witch. 3 times 1 is 3. 3 plus what is going to give me 7? That's got to be 4. So I made it work. I made it work for that one, but I can't say that this is true until it works for every one. 3 times 2 is 6. 6 plus 4 is 10. 3 times 3 is 9. Plus 4 is 13. 3 times 4, you get it, right? So we see it work. So now I can be confident that this equation is what I need it to be. Why did I come up with the equation? They just asked me for the 15th term, Dion. Why didn't I just count up? Which you could have done. You could have totally counted up. But the reason why the equation is really helpful is because usually when you're asked questions like this, they'll be like, what is the 950th term? You don't want to count up that high. So oftentimes having an equation is really helpful. So what term are we looking for? We're looking for the nth term, and that nth term in this case is the 15th term. So I'm going to take my handy dandy equation, and I'm going to say t, the term that I'm looking for, is equal to 3 times 15 plus 4. We all know how to calculate this. 3 times 15 is 45. When I add 4 to that, I get that t is equal to 49. So if I continue this process, I'd get all the way out to 49. Isn't that special? I hope you liked it. I loved it. All right, let's look at our last example for this lesson. There's no real words here, but I'll talk to you about what this really means. So basically, this problem is saying, hey, if you go to a dinner, sometimes at a dinner, you'll have a beautiful table, and it can only seat 4 people. But if you put 2 tables together, you can, I should have done that in red. If you put 2 tables together, you can seat how many people? 6 people, right? What happens if we put 3 tables together? Let's try it out. So 3 tables together, we now can seat 1, 2, 3, 4, 5, 6, 7, 8 people. The question is, how many, I don't remember what the question was. The question is, okay, I got it. The question is, how many tables do we need to seat 16 people? And yes, this is an arithmetic sequence for a real life situation. So let's go ahead and set up our handy dandy chart. So I'm going to get started with that right away. Okay, so I've got here how many tables needed for 16 people. That's our question that we need to keep in our mind. And I've started putting it into a table with tables as one thing and seats as another. So for 1 table, 4 people, 2 tables, 6, 3 tables, 8, 4 tables. Can you guys kind of guess what 4 tables would be? It would be like 1, 2, 3, 4. 1, 2, 3, 4, 8, 9, 10. So it would be 10. And that's not the color I wanted. So you might be able to start to see a pattern. And so what we're going to do is, I hope you realize that this really does look like an arithmetic sequence. How come? Well, we can check the change from tables to tables. That's consistent, like 1, 2, 3, 4. It just goes up 1. And here the change for seats seems to be increasing by 2, right? So we've got 2, and our expectation is that will be 12, and that seems to make sense. Even if we were to draw a picture, we'd see that. So the question is, how many tables would we need for 16 people? Certainly we can continue on, and it would be a very few more input-output values that we'd have to put in here to continue on and see the answer. But of course, I'm going to ask you to do an equation. So let's do an equation. So let's let t, let's let t be the number of tables and s be the number of seats. And so what we notice is the relationship, as the tables increase, as each table increases, I get 2 more. So that should first tell us that the common difference is 2 for this arithmetic sequence situation, right? And the next thing is that from our last couple of examples, we realized that we can think of 2, last time it was n, but we'll do 2 times t, since the tables, or t is in the n's place, like as we had in the last situation. So 2t is somehow going to be equal to the number of seats available in this situation. But obviously 2 times 1 is not, s is not 4 in this case, but 2 times 1 plus 2 might just work. I can't say that this works until I check it for everything. Let's try it out. 2 times 2 is 4, plus 2 more is 6. 2 times 3 is 6, plus 2 more is, yay, 2 times, yay, 2, yay. Okay, so we're feeling good. Our equation is as follows. So 2t plus 2 is equal to the number of seats. I put seats out there. So I'm going to use my equation to solve this problem. So how many tables would be needed for 16 people? 16 people means 16 seats. So I've got 16 is equal to 2t plus 2. And with a little bit of algebraic manipulation, I'm subtracting 2 on both sides, doing my thing, I get that t is equal to 7. So I need 7 tables. Hooray! All right, we did that under 15 minutes. I know it's kind of a long explanation, but I hope it made sense. I look forward to seeing you guys tomorrow. Please let me know if you have any questions, and have a good day. All right, bye-bye.